right, in this video, we're going to go ahead and solve a two-dimensional collision problem. This is an elastic collision, not an inelastic collision. That's one of the problems with saying we're doing an elastic problem. It sometimes sounds like inelastic. So here we have two objects, 1 and 2. I've actually color-coded them, so object 1 is in blue, object 2 is in red. We see that initially object 1 is moving with a speed of 3 meters per second. I'm going to go ahead and write that in. Let me go ahead and get my pen ready. So V1 is going to be 3.0 meters per second. I'm going to give it a direction of I hat. And it collides with object 2, which is initially at rest. So V2 is going to be 0 meters per second. Notice that they both have the same mass, so M1 equals M2, which is going to be equal to M. I'm just going to use M for the equation. After the collision, object 1 will move with an unknown speed at an angle of theta 1, which is going to be 30 degrees. Object 2 will move with an unknown speed and another angle, as seen here, and I've defined this as 50 degrees. We want to find the speed of each of the objects after the collision. So we want to find the final speed of object 1 and object 2 after the collision. I see here that I have angles, and that means that I need to break them up into components. Anytime an angle is given and you're dealing with vector quantities, you're going to need to break it up into components. So the first thing I'm going to do is I'm going to go ahead and draw V1. Keep in mind I'm not going to be a pro at this, but we'll just go ahead and hopefully get as close as possible. So that is V1. I'm going to go ahead and draw the x-axis here and the y-axis. And I'll go ahead and move my vector to match up with my X and Y axes there. I'm also going to change the color here so that we can see it a little bit better. There we go. Okay, now I'm going to go ahead and draw the components. I'm going to make the components just a different shade. So notice that this will project down and it will also project horizontally. I'm going to straighten this out a little bit so it actually looks like it's there we go. It's one of the problems with using the software here is that it kind of locks into position and it doesn't really let you change it. There we go. That's great. The angle here is going to be the 30 degrees. This is going to be your V1 final. I'm going to erase that and try, I'm going to use something a little bit different. I'm actually going to use V1 prime because once you start getting the subscripts in there with the X and the Y direction, you're going to end up with too many subscripts and it might get confusing. So for after the collision, instead of using F for final, I'm going to use a prime to indicate after the collision. Okay, so that's going to be my final velocity after the collision for object 1. This is going to be the Y component, V1Y prime, and this is going to be V1X prime. Now, we know that whenever we need to break a vector into components, we need to use sine and cosine. So the first thing I'm going to do is define sine. So sine theta 1 is going to be opposite over hypotenuse. That's going to be V1Y over V1, and that's going to be primed, both of them. That means that my Y component is going to be equal to the V1 prime times sine theta 1. Okay. Cosine theta 1 is defined as adjacent over hypotenuse. This is the adjacent side, so this is going to be v1x prime over v1 prime. And that means that the x component is going to be equal to v1 prime times the cosine of theta 1. I'm going to write that using vector notation. So v1 prime is going to be equal to, looking at this, I have v1 prime cosine theta 1 I hat plus v1 prime sine theta 1 j hat. Now I'm going to do the same thing for the second one. Let's go ahead and draw the line for the second one, and I'm going to go ahead and give it a different color. Actually, we'll use this. Let's use a different color so we can actually see the difference. There we go. And so this is, I'm going to try and match it up exactly. There we go. And then I'm going to draw out my x and y axes. Okay, now in order to draw the components, I'm going to change the color just a little bit. This is going to be my x component, and this is going to be my y component. Remember, all I have to do is project it onto the x-axis and project it onto the y-axis. I'm going to move this up just a little bit. There we go. It's not quite straight, but it will do. This is going to be the 50-degree angle. This is going to be V2 prime. This is the x component, so this is the V2x prime, and this is going to be V2y prime. Okay, I'm going to start with sine theta. Sine theta 2 is going to be opposite over hypotenuse. So that's going to be V2y prime over V2 prime. And that means that V2y prime is going to be equal to V2 prime times the sine of theta 2. Now we're going to use cosine theta. Cosine of theta 2 is going to be adjacent over hypotenuse. That's going to be adjacent over hypotenuse. So that's going to be V2x prime, oops, V2x prime over V2 prime. Solving for V2x prime is equal to V2 prime times the cosine of theta 2. I know it's a lot of work, but it's really important that we break our vectors into components because we can't add together angles that are not the same, right? The vectors have to be either parallel or anti-parallel to be able to numerically add them. All right, so let's write this out in I hat, j hat notation. We have V2 prime is going to be equal to the x component. Now notice it's going east. So that's V2 prime cosine theta 2 I hat. But notice that the y component is going south. So that's going to be minus V2 prime sine theta 2 j hat. Okay? So now that we have the velocity after the collision broken up into components, we can now go ahead and solve for our conservation of momentum. Conservation of momentum tells us that the momentum before a collision must be equal to the total momentum after the collision. So in other words, the momentum initially that we start with has to be equal to what we end up with, as long as we have a closed isolated system, which we do in this example. Okay, we also know, though, that these are vector quantities, right? And we can't add I hats and j hats together. So there's two ways to solve this. I can add them all together and then separate the i's and the j's, or I can just separate it to start with, like you do with Newton's laws, and I'm going to do that. So I'm going to first solve this problem doing the sum of the momenta in the x direction. So right here, we're going to do the sum of the initial momentum in the x direction must equal the sum of the momentum after the collision in the x direction. Okay, so let's look at what we start with in the x direction. If we look at our picture, we can see that we have the mass of 1 times its velocity. So let's go ahead and write that out. So we have m, remember, because m1 is equal to m, v1 plus mv2, and I'm going to put subscript x's here, has to be equal to mv1 x prime plus mv2 x prime. Now, looking at your picture here, you can see that ball 2, sorry, is at rest. So that means that this term is 0. Notice also that all the terms have m. So if I divide both sides by m, I end up with v1x is equal to v1x prime plus v2x prime. Now I can substitute in the x components and get rid of the subscript x's. All right, so this is going to be mv1, and that's going to be equal to, I'm sorry, get rid of the m, we already did that. So this is going to be v1, and that's going to be equal to v1 prime. Now the x component is going to be the cosine theta. So this is going to be cosine theta 1, and I'm going to have to give it a direction, so I'm going to give it I hat. And if we look at the x component of 2, that's right here. Notice that that is v2 prime, so plus v2 prime cosine theta 2, and that's also I hat. All right, if I write this without the vector sign, I end up with v1 is going east, and that's equal to v1 prime cosine theta 1 I hat plus v2 prime cosine theta 2 I hat. Yes, I could have written it this way to start with, and I probably should have. Now I can cross out all the unit vectors. I'm just dividing all terms by I hat. And now I have v1 is equal to v1 prime cosine theta 1 plus v2 prime cosine theta 2. Now I have two unknowns. I don't know, right here, I don't know v1 prime and I don't know v2 prime. So this means that I'm going to need another equation, right? So now I'm going to go ahead and do the y direction. So let's go ahead and do that. The sum of the momentum initially in the y direction has to equal the sum of the momentum final in the y direction. Now, if I look at my picture, I can see that I don't have any momentum to start with in the y direction, right? It's only going east. So that means that this whole term is 0. So let's go ahead and do this. We have 0 is equal to, now let's add up the y components. We have this v1 prime sine theta 1 j hat, and we have negative v2 prime sine theta 2 j hat. So let's go ahead and write that out. v1 prime, sorry, that has to be sine. Sine theta 1 I hat minus, sorry, j hat. I'm getting a little confused here. Plus v2 prime, actually it's a minus because it's going south, sine theta 2 j hat. I can add this term to both sides. And I end up with v2 prime sine theta 2 j hat is equal to v1 prime sine theta 1 j hat. Notice that the j hats can be canceled out. It could have been done up here as well. So now I have my two equations with my two unknowns. Here I have v1 and v2. Here I have v1 prime and v2 prime, the same as here. Sorry, I missed the primes on that one. So there's two ways to do this. I can do substitution, elimination, or linear systems. I'm going to do substitution. So what I'm going to do is I'm going to take this equation and divide it by sine theta 2. Okay. And now I have v2 prime is equal to v1 prime times sine theta 1 over sine theta 2. Okay, and I'm going to leave it as is. I'm not going to substitute any numbers in yet. I'm going to substitute this into here. Okay, so notice here, this is the same thing as this. So let's go ahead and substitute. We have v1 is equal to v1 prime cosine theta 1 plus, substituting that in, v1 prime sine theta 1 over sine, I'm messing it up now. Sine theta 2 all times cosine theta 2. Some of you may be saying, oh, well, that can be sine theta 1 divided by tan theta, tan theta 2, that's true. Or it could be sine theta 1 times cotangent theta 2. That's also correct. I'm just going to leave it as is. Okay, so notice here, v1 prime, v1 prime. I can factor that out. So now I have v1 is equal to v1 prime times cosine theta 1 plus sine theta 1 cosine theta 2 over sine theta 2. And now I'm going to divide both sides by this term. Cosine theta 1 plus sine theta 1 cosine theta 2 over sine theta 2. And I'm going to divide this side by the same thing. Okay, and now I get v1 prime is equal to v1 divided by cosine theta 1 plus sine theta 1 cosine theta 2 all over sine theta 2. There are advantages to solving the problem without putting any numbers in. And the reason that we do this is that it gives us a better understanding of a generic problem, right? What if the angle's not 30 to start with? What if it's 45 and 45? Well, now I have an equation and I don't have to resolve it again, right? So the advantage of using variables instead of putting your numbers in right away is that if for some reason you need to change one of these variables in the next part, or let's just say they say, oh, well, that's a 30 degree. What happens if I make it a 25 degree angle? Or what if I make it a 50 degree angle and the other angle is different? then how will this look? So it gives you the freedom to be able to solve the problem multiple or one way and then use this equation multiple different ways. Okay, so now we're going to put in our numbers. So I believe it was 3.0 meters per second over the cosine of 30 degrees plus the sine of 30 degrees times the cosine of 50 degrees divided by the sine of 50 degrees. Okay, so now I'm going to get out my calculator. Let me find my calculator. Okay, so we take 3. Actually, what I'm going to do is this. It's going to be easier for me to calculate the denominator, and then I'm going to invert it in my calculator. But what I'm going to do for you guys is I'm just going to solve the denominator first, and then I'll show you what to do. Okay, so I'm going to do this term first because that looks nasty. Okay, for my calculator, I have to put in the angle first and then choose the function. So the sine of 30 degrees is 0.5 times the cosine of 50 degrees. Okay. And then I'm going to divide that by the sine of 50 degrees. And then I'm going to add that to the cosine of 30 degrees. Okay, so we get, for this bottom piece, 1.28. And I'm sorry, I made a mistake on the little doohickey thing. Actually, I made a mistake on the number of sig figs. Hold on. We're going to make this 1.3. Nope. There we go. Okay, so what I'm going to do is I'm going to invert this and then multiply by 3. Okay, and that means that my final speed after the collision is going to be 2.3 meters per second. Okay, and that's for 1. Now, in order to find V2 prime, I already have the equation right here, right? So I'm just going to take this equation and write it down here. Okay, so this is going to be 2.3 meters per second times the sine of 30 degrees divided by the sine of 50 degrees. Let's put that in our calculator. Okay, so we have 2.3 times, oops, that's not right. 2.3 times the sine of 30. So I'm going to type in my angle first, find the sine of that, equals, and then I'm going to divide by the sine of 50. And I get 1.5 meters per second. So V2 prime is equal to 1.5 meters per second. And there you go. That is solving for the final speed of ball 1 and ball 2. Now, if I did have to find this angle here, I would need a third equation. because this is elastic collision and elastic collision, I could then use energy conservation to come up with my third equation. So remember that for elastic collisions, your energy is conserved. So that means that I'm going to put energy conservation. So this tells us that the total energy we start with has to equal the total energy we end with. And that means that all of the kinetic energy for 1 plus all the kinetic energy for 2. Oops, let me get rid of that. Should be a squared, not a prime. Has to be equal to the total kinetic energy after the collision for both. Okay. Notice here how all the 1/2s cancel out and all the masses cancel out. We also know that this term here is 0. Right? So this makes it actually a little bit straightforward. So now we know that V1 squared is equal to V1 prime squared plus V2 prime squared. And that's a third equation that you could use. All right, so this is a third equation you could use to solve for a third unknown. So I'll just add that in there. All right, there you go. I hope you've learned a lot about how to solve a collision problem in 2 dimensions.